We're going to have to use conservation of mass. Uh, Conservation of energy, or if we simplify that, Bernoulli's. And then, you know, we have a manometer down here, so we're gonna have to use the manometer equation. So let's take a look at this. Let's start. Um, Really, you can start this problem off using any of these, um, and then just plug in what you get in another equation. It doesn't really matter what you go in. But I'm going to start off here with Bernoulli's. So Bernoulli's equation. Let's read the problem first. It says if the difference in the level of mercury within the manometer is 80 millimeters, determine the volumetric flow of the water. And then it says take the density of mercury be 13,550 kilograms per meter cubed. We have some information from the picture. So our diameter at B is 100 millimeters. Our diameter at A is 40. Our uh, height difference in mercury, our pressure difference is 80 millimeters. That's kind of all we know from the picture, all we know from the problem statement. So let's get started and see what we can do. So Bernoulli's, again, I think that's how you write it. Um, so our entrance is B, so I'm going to put PB over rho plus VB squared over 2 plus GZB equals PA over rho plus VA squared over 2 plus GZA. Um, so we're on the same streamline. So the height difference between point B and point A is 0. So we can get rid of our potential energy term. So GZB and GZA are equal to 0. Um, that's about all of the simplifying that we can do. Um, we have a pressure here, right? Because this is just a cut out of our tube, and this is also just a cut. You could see with the squiggly line, this is just a cut out of our pipe. So we have pressures at both B and A. So we have to keep those terms. We have a velocity at B, we have a velocity at A. We're not really told otherwise. So we have to keep those as well. Um, so we are looking to find volumetric flow. So if you remember what volumetric flow is, it's Q equals VA. So we know the areas, so we're good with that, but we're looking for a velocity. Now it could be the velocity at B or it could be the velocity at A, or yeah, at A. So let's try to solve for the velocities here. So we're going to say PB minus PA over rho equals VA squared minus VB squared over 2. And that's all we can do, right? We don't know any pressures, we don't know any velocities. The only thing we know is the density here of water, but it's not really going to get us very far. So let's use another equation. You can either go with the manometer equation or you can go with conservation of mass. I'm going to go with the manometer equation for right now. So manometer equation, So I don't really remember what chapter this is from, maybe two, three, probably two. Anyways, so if you remember from earlier in the semester, we're going to take, or at least this is how I solve it. I'm going to take a cut down the middle. I'm going to say that everything on the left side here has to equal the right side. So let's see, let's start with the left side. So at the left side, we have a pressure of B. And if you remember, manometer equations have to deal with pressure. So this is what we're dealing with when we're talking about the manometer equation. So the pressure at B plus, if you remember, um, rho GH. So rho GH equals pressure. So this could be from any type of fluid. In this case, on the left side, we have a height of water. So rho H2O times G times the height of water. So our height of water is from this line here all the way up to our streamline. So we know that from here to here is 0. What is that? 0.08 meters. And from here to here is 0.05. And this just comes from the half of the diameter, so our radius. So 0.05 plus 0.08 equals 0.13. And then we're going to set this equal to our right side. So now we're working from this side. And on the right side, we have PA plus rho H2O times G times the height of water. So our height of water here is from this line to our streamline. And if you remember from this side, that is just going to be 0.05. Okay, so 0.05 here. And then we also have some height of mercury here. So that's from here to here. That's 80 millimeters. So we're going to say the rho of Hg times G times 0.08. Okay, that's a little messy, but that says 0.08. So if we simplify this, right, let's try to find this term here, right? The pressure difference. So to do that, we're going to say PB minus PA equals rho H2O times G times 0.05 minus 0.13 plus rho Hg times G times 0.08. And then we know all these terms, right? We know the density, we know gravity, we know this height, we know the density of mercury, we know the density, or we know G, and then we know the height. So everything here is known. So this is going to be, uh, if you work this out in your calculator, right? The density of water is 1,000 uh, kilograms per meter cubed. G is 9.81 meters per second squared. Height is the difference here. Uh, the density of mercury is 13,550. G again is 9.81. And this here is 0.08. So if we work this out, PB minus PA should be around, and if you get a different number, you know, this is just what I have from an earlier session. So it's about 9,849 pascals. Get a little more, a little less, that's fine. So now we know the pressure difference, right? Um, so we know our pressure difference. We can put this back into this equation up here. So we can say PB minus PA is 9,849 over rho equals VA squared minus VB squared. over 2. So we know density, we know this value here. The only two that we don't really know is VA and VB. We'll solve that using our conservation of mass. So if you guys remember conservation of mass, I'll write it over here, conservation. After you make all your assumptions, right, it's going to be rho VA in equals rho VA out. Now you have to be careful about your assumptions, right? I'm just saying after you make all your assumptions. But in this case, right, you have to really be careful about how you read the problem, and you have to know what assumptions you're making. So here we know um, we're not told that this is anything but steady state. We we're not told that we have a non-uniform velocity profile. So we know that we have steady state. We know that we have a uniform velocity profile, and we're not told that our densities are changing. So, we can make, the we can make those assumptions and have this equation. But again, be very careful when you're reading your problems. So rho VA in equals rho VA out. Because our densities are the same, we can cancel them. So VA in equals VA out. So we can say our in is at B. So VB times VB times AB equals VA times AA. And now we can solve for one of these terms, right? And we're going to plug it in up here because right now we have two unknowns, and we're going to use one more equation to bring that down to one unknown. So this is the equation that we're using here. So we're going to say VB equals VA times AA divided by divided by AB. So uh, we know areas, we can find the areas, so that's not really a problem. So let's go ahead and do that. So the area at A, like before, area at A equals pi d squared over 4. The area at A is, or the diameter at A is 40. So this is going to be pi times 40 over 1,000 squared over 4. And this is going to be equal to 0.00126 meters squared. We're going to do the same thing at B. So AB equals pi d squared over 4. Our diameter is 100 millimeters, so that's 0.1 meters, but I'll just write it down here as pi 100 over 1,000 squared over 4, and we're going to get 0.00785 meters squared. So if we come back down and plug that into this equation, we're going to have VB equals VA times AA, which is 0.00126. So just give me a second here. 0.00126 divided by 0.00785, so 0.00785. So let me just plug that into my calculator real quick. And you should get that VB is equal to about 0.16 VA. So now we can plug this into here. So that's exactly what we're going to do. So we're going to say 9849 divided by rho, which is 1,000, is equal to VA squared minus 0.16 VA squared over 2. And if you do this, you're going to get um, that this term here is equal to 0.0256. So you're going to do 1 minus 0.0256. So this is like our 1. So we're going to do VA squared minus 0.0256. This is a minus 256 VA squared over 2. And you should get um, 0.4872 VA squared equals 9.849, which is just this term here, right? 9,800 divided by 1,000. And then if you multiply or divide by 0.48, you're going to get, and then you take the square root of that, you're going to get VA equals about 4.496 meters per second. So that's our velocity. And we're being asked to find uh, volumetric flow. So if you remember volumetric flow, Q equals VA. So we know area, we know velocity, so we can find volumetric flow. So that's going to be 4.496 meters per second times the area at A. So don't do area at B. We found A, we found the velocity at A, so just use the area at A. So that's going to be 0.00126. So 0.00126. And once you multiply that, you're going to get volumetric flow to be 0.00567 meters cubed per second. So that's the answer. If that